So this is for networking class, programming assignment 4, simulation 3. So we're essentially tasked with creating this network. This simulation highlights kind of our distance vector protocol and transferring packets from different routes on different routes from different hosts. So essentially what we need to do is set up so that host 1 sends on a different route than host 2 does. So the way we did that is we have the cost from each path from host 1 to host 2 be the same, but the individual links on those paths are different weights, essentially so that when it gets to either router A or router D, to decide which path it travels on, it'll take the greater of the two first. So the way that we set up our network is we have cost 1 from host 1 to router A, cost 1 from A to B, cost 2 from B to D, and cost 1 from D to host 2. On the other path we have cost 1, router D to router C is cost 1, router C to A is cost 2, and then A to host 1 is cost 1 again. So essentially what happens, we originally planned so that it would take the least first, but it was easier to implement to take the greater of the two paths first. So we have host 1 go to A, and then when it sees that it's the same distance on either path to host 2, it will pick to go to router C because router A to B is 1 and router A to C is 2. So it takes the bigger cost one first, and then it will go to router D and then host 2. So to show this, I'll run this. As I said, this also highlights our router mapping protocol, because this network is a lot more complicated, but it still works. So from the start, if we can find it right here, this is the original tables, pretty much the router and what it knows it can get to, aka its neighbors. From there, what happens is each router will send the tables to all of its neighbors, and they'll update, and every time they update they will send their updated tables to their neighbors again, until the network has kind of stabilized itself. So we see a lot of these come up just because it has a lot more updates than the simple network that we were working with earlier. And then we come up with the last 4 that are complete tables that can get to every other destination as modeled in our network. So router A is there, router B, router C, router A again, so router D must be up here somewhere too, router D right there. Yeah, so those are our final ones. If you want to look to check these network costs are there, they're up here. So then to prove that we travel from different paths, we have a message being sent, and I don't see where it's being sent, but receiving, okay, here we go. So we are forwarding a packet that's a message from H1, host 1, to router A. Essentially, router A will then forward to router C at cost 2. And we can see that in our table from router A to host 2. We know it's going to take us 4, but we know we can either travel to router B, which is a 1 cost, or router C, which is a 2 cost. Since each of these paths are the same in our actual table, which is up here and looks something like this, the end values will be the same, but router A decides to take the heavier path first. Then once we're at C, we can traverse to D at cost 1, and then, yeah, that's right here, C to D at cost 1, and then D will forward to host 2 because it has a direct link to that. Then host 2 sends its return packet. Router D, it sends it to router D, and then in router D table, we know we can get to host 1 right here at cost 4. We can either take router C first or router B first. B is the heftier of the two, so we know we're going to take that right here. So host 2 to router D, we take the cost 2 one, which is to router B, which proves that we take a different path. And then router B goes to router A, and router A forwards to host 1. And host 1 receives that right here. So there is our proof of different paths forwarded, and also that our tables converge in Simulation 3.